I'd like to say a few words about the Knoevenagel condensation. The Knoevenagel condensation is kind of like a crossed aldol in that we're using two different compounds or reacting two different C double bond O compounds. But the difference here is that one of the C double bond O compounds is a dicarbonyl compound, specifically a beta dicarbonyl compound that allows for the production of that very stable anion we talked about with the acetoacetic ester and malonic ester syntheses. Remember, the anion that we get from this is going to be stabilized by two carbonyl groups, which makes the hydrogens in the middle here very acidic, certainly much more acidic than any hydrogens we might see on a regular carbonyl compound. As two ways you might see this reaction represented. First one, you'll see a beta dicarbonyl compound and then a base, and that's to remove the protons, and then the addition of the other aldehyde or ketone, and then the addition of H plus to work up the reaction. The other way of seeing it is with the base already added, so the anion's already formed, and then we add in the aldehyde or ketone, and we still get the H plus to work up the reaction, and we still get the same product. All right, I won't really be discussing the mechanism here. Let me give you some more examples. And here's two examples of how we could represent the reaction, just following what I was just saying. So again, we have the beta dicarbonyl compound, the base to form the anion, followed by the addition of the carbonyl compound and then H plus at the end. The other way of seeing it would be to have the anion already formed, that is without the base there, and then to add the aldehyde or ketone and then to add H plus, and we get this product here. You'll see the compound does follow the same, the Knoevenagel condensation follows the same pattern as the other aldol condensations we've looked at. And what happens is we always choose the beta dicarbonyl compound to be the source of the alpha hydrogens, because that's where the hydrogens are going to be removed from. This is true even if the aldehyde or ketone we're adding to it does have alpha hydrogens. It'll always come from here. Alright, so that would give us this product. And you can see in this instance that since we have the same group attached to the carbon, the same carbon of the double bond, that we don't have any cis or trans isomerism in this case. So that's how that would work out. Let's look at another one, just showing you the pattern here. So again, we know this is going to be the source of our alpha hydrogens, and then we're going to add our aldehyde or ketone, in this case an aldehyde, throw them together, and what we end up with is a compound that will indeed have cis and trans isomerism. So I will attach squiggly lines to these to indicate that both cis and trans are possible. Remember, the squiggly lines can be added to either the top or the bottom of the CC double bond. Doesn't matter which. All right, that's one example. I'll show you one more example. And again, we know that the two hydrogens will come from the dicarbonyl compound. And here we've got another aldehyde or ketone, in this case an aldehyde. And you can see that we do have the possibility of having another set of alpha hydrogens here, but these alpha hydrogens are nowhere near as acidic as these here. So we do the same pattern. And what you can see here is that we have, again, symmetry about the carbon, this carbon of the double bond, which means that no cis and trans isomerism is going to be possible. And that's how we would represent the product.